Question 11 asks you to state the trapezoidal rule and then use it with 6 strips to determine approximate value of the definite integral for the curve f of x equals 4 times x minus 3 all squared from x equals 0 to x equals 3. And importantly, in the wording of the question, it asks you to show all substitutions that are made into the rule. So firstly, the trapezoidal rule is a technique for numerical integration. In other words, for approximating definite integrals of the form from x equals a to x equals b of f of x dx. Let's first of all outline the solution and then show you how TI-nspire can be used to answer the question. So we're given a function f of x equals 4 times x minus 3 all squared. So that's a positive parabola with a turning point at 3, 0. And you're asked to use the trapezoidal rule with 6 strips from x equals 0 to x equals 3. From the formula booklet, the trapezoidal rule formula, you'll need to state this working in your solutions, that definite integral is approximately equal to w on 2, where w in this instance is 3 minus 0 over 6, so it's like, if we'd like to call it the width of the strip, times these particular function values, and they're built upon the 6 trapezia that are being used. So you've got, at one end, you've got your function value f of 0, and at the other end, you've got your function value f of 3. In the middle, you have f of 0.5, f of 1, f of 1.5, f of 2, and f of 2.5. And the 2's really are representing the fact that you're counting those function values twice because you've got adjoining trapezia. Okay, so what you need to do is you need to evaluate each of these at x equals 0, x equals 0.5, etc., up to x equals 3, and then those values are substituted into the function that will give you these function values here. Okay, so what we've got here is we've got that it's equal to a half times a half. So that half corresponds to the w on 2 is basically a half times a half, multiplied by f of 0 is 36, plus 2 times f of 0.5, so we get 2 times 25, all the way through to f of 3 is equal to 0. And then what you need to do is just evaluate that expression, and the approximate area that you obtain is 36.5 square units. So you'll need to write all that down to achieve full marks for this question. Let's have a look at how TI-nspire can assist in the solution to the question. Now, I think it's a really good idea here to assign f of x to be that quadratic, and that's what I've done here. So to show you how to do that, all we need to do is we say, okay, we'll type in f of x like so. Now the assign command, it's small and it's in red and it's above the symbols template key. So if you press Control symbols template, that will give you access to the assign command, and then you enter 4 times x minus 3 all squared as shown up the top there, and then press enter. The next entry line, I've created a list of those function values that I can show you again back on page 1.2 here. We can represent f of 0, 2 times f of 0.5, all the way up to f of 3. We can represent those values as a list. you can tell it's a list because you have a curly parenthesis or a curly opening bracket, and as a match, you have a curly closing bracket. Now, to access that, what you would do is you would press Control and then the normal closing bracket key. And that is how you begin to create a list. And then what you would do is you would enter each one of these separated by a comma. So I'll start it off. For example, you would first of all enter f of 0 and then use the comma key. And then you would type in 2 times f of 0.5. And you would continue on until you get to f of 3. Once you've done that and you press enter, this gives you the values 36, 50, etc. down to 0. And they're the values that are listed in this line of working here. And a clever way to find the sum of elements in a list is to use the sum of elements command. So basically, if we go back to our working, that a half times what's inside that square bracket there corresponds to this entry line here in TI-nspire. So first of all, you type in a half times a half times. Now, to access the sum of elements command, what you would do is you would press menu, then 6 or enter for statistics, then 3 for list maths, and then number 5 is sum of elements. So that's how you access the sum of elements command. And then basically what you would do is you would inside that, so if I just quickly spell SUM, you can also do that on your keypad and open bracket there. What you can do is you can go up to the previous entry line and highlight it and then bring it down to the current entry line by pressing enter. Now I neglected to have the half times a half there. I'm just showing you how to paste the elements in that list into the sum of elements command. So that's how you would quickly do that. And when you perform that calculation with TI-nspire, you get an approximate answer for that definite integral of 36.5, which corresponds to the 36.5 we obtain in our solution there on page 1.2. So let's now have a brief think about the answer. You don't need to do this for the solution, but it's not a bad technique of checking at least the type of answer that you get. When you calculate the definite integral from x equals 0 to x equals 3 of f of x dx, the actual answer, or the actual area, is 36. And our estimate was 36.5. And so our estimate overestimates the proper or correct area. Now, when we use the trapezoidal rule, we need to think about the concavity of the curve. And we've got a positive parabola, which means that the curve is concave up, which means that the second derivative is always greater than 0. In fact, if you differentiate f of x twice, you get an answer of 8, and 8 is greater than 0. And if the curve is concave up, then the trapezoidal rule overestimates the area. And our estimate of 36.5 does indeed overestimate the actual area, 36.5 being greater than 36. So that at least gives us a good foundation to say, okay, I think that I've obtained the correct answer because I've got an overestimate. Now, I wouldn't advise you to do this in the exam per se, but it's nice to be aware of that there is an alternative form for the trapezoidal rule. And so the definite integral of f of x dx from x equals a to x equals b is approximately equal to w, which is the width of the strip, multiplied by f of x naught, which in our instance would be f of a, plus f of xn, which is f of b, all divided by 2. So in our example, it would be f of naught plus f of 3 divided by 2, plus a sum from I equals 1 to n minus 1 of f of xi. And basically, that's the sum. We go back to page 1.2. That's the sum of these function values that have a 2 as a coefficient. So basically, it's separating the two end function values and then summing the other function values, each multiplied by 2, because we've got adjoining trapezia. So this is quite fancy, and you may not need to do this in the exam, but it's worthwhile having a look at this outside the exam. You can assign A to be equal to 0, and you can assign B to be 3, and we're using the control symbols template for the assign command. We've got 6 strips, so you can assign N to be 6. Now W, the width of each strip, is equal to B minus A over N, so you can assign that. So we've got A is 0, B is 3, N is 6, W is a half. And we can also assign this right-hand side here as a function. And so I've called it T rule, which is short for trapezoidal rule. And I've assigned it again by using the control symbols template. It's the colon equals. Now, to get a decimal answer, what I've done here is I've started with the approximate command. And how you find the approximate command is if you go into your catalog and then press 1 to enter the A to Z part of the catalog, and then scroll down, you find the approx or approximate command, and the syntax is approximate value. So it's approximate, makes it a decimal. The width multiplied by f of a plus f of b all over 2, plus the sum from I equals 1 to n minus 1. So if n equals 6, we've got the sum of 5 function values. And if we go back to page 1.2, we can see we've got 1, 2, 3, 4, 5 function values which relate to those adjoining trapezia. So that's why it's n minus 1 of f of a plus I times w. So to get the sum command, what you would do is you would press menu. It's a different sum command, this one. Menu calculus, number 3 for sum. And then what you would do is you would enter I equals there, I there, 1 there, n minus 1 there, and here you would type in, with the function defined or assigned, f of a plus iw. Okay, so I'll just get rid of that. And this next line here is basically stepping out what this formula does. Now, in the question, remember it says, if we go back to page 1.1, show all substitutions made into the rule. So if you don't do that in the exam, it appears quite strongly that you won't get full marks. So just be careful or cognizant of that. But the way this formula is working is we're saying, well, okay, W is a half or 0.5. f of 0 plus f of 3 all over 2. And now let's unpack this. This is saying f of 0 plus 1 times 0.5 plus f of 0 plus 2 times 0.5 plus f of 0 plus 3 times 0.5 plus f of 0 plus 4 times 0.5 plus f of 0 plus 5 times 0.5. And when you enter that in and press enter, you get 36.5. So that's showing you how this formula works. So as I said, the best way to do this question is showing you're working on page 1.2 and using Inspire in this way on page 1.3. But if you wanted a checking device, you can also do the question in this way primarily as a check. In question 12, we're told that the magnitude of an earthquake can be modelled by the logarithmic equation m subscript a equals log to the base 10 of I subscript a on I subscript 0, where m subscript a is the magnitude of the earthquake at a location A, I subscript a is the intensity of the earthquake at location A, and I naught is just a constant. So an earthquake at location P had a magnitude of 5.2, and at a different location Q, a different earthquake had a magnitude of 3.5. There's two parts to this question. Part A asks us to determine an equation involving logarithms that expresses the difference in magnitudes between the earthquakes at location P and Q. So that means we need to find an expression for MP minus MQ. So that's part A. We'll come back to part B in a moment, but part B says or asks us to find or to determine how many times more intense was the earthquake at location P compared to or than the earthquake at location Q. So in part B, we're asked to compare the earthquake intensities at P and Q. So let's first of all work on part A. It's a 1-mark question, and you cannot use your Inspire for this. This is by hand or pen and paper mathematics. So at P, m subscript P is equal to log to the base 10 of I subscript P on I naught. And at Q, the magnitude MQ is equal to log to the base 10 of IQ on I naught. It's just a matter of forming the difference between those two. So the difference in magnitude between the earthquakes at P and Q is given by MP minus MQ. And all you need to do is just write that that's equal to log to the base 10 of IP on I naught minus log to the base 10 of IQ on I naught. In part B, we're asked to compare the intensities of the earthquakes at P and Q. Now we need to do some by hand mathematics. The TI-nspire helps us with a numerical calculation at the end. So basically, in going from this line here to the first line of part B, what I've done is I've used the log laws, and I've used the important log law that, for example, log A minus log B is equal to log of A on B. So in other words, we've re-expressed MP minus MQ as log to the base 10 of IP on I naught divided by IQ on I naught. And we can simplify the right-hand side there by noting that the I naught, which is the constant, that cancels. And so we can simplify the difference MP minus MQ and write it as log to the base 10 of IP on IQ. Now, what we need to do is we need to get an expression for the intensity of the earthquake at P in terms of the intensity of the earthquake at Q. So in other words, we need to obtain IP in terms of IQ. So in moving from line 2 to line 3, what we're doing is we're exponentiating. We're raising both sides to the power of 10, if you like. And so we can therefore, and they've swapped sides. All right. So the MP minus MQ, that becomes 10 to the power of MP minus MQ. And 10 to the power of log to the base 10 of IP on IQ, 10 to the x and log to the base 10 of x are inverse functions of each other. And so 10 to the power of log to the base 10 of IP on IQ will just give you IP on IQ. Now, we are given in the question, if we go back to the question, the earthquake at P had a magnitude of 5.2, which means that MP is equal to 5.2, and correspondingly MQ is equal to 3.5. So MP is equal to 5.2, MQ is equal to 3.5, and so we can make that substitution into line 3 to obtain IP on IQ is equal to 10 to the power of 5.2 minus 3.5, which gives us 1.7. So we're nearly there. What we can do now is we can multiply both sides of this equation by IQ. And so IP is equal to 10 to the power of 1.7 times IQ. Now we're going to evaluate 10 to the power of 1.7 on TI-nspire in a moment. I've already done it, obviously, and we obtain 50.1187 ... And so we can therefore substitute, instead of 10 to the power of 1.7, we can substitute 50.1187, etc. And we can therefore conclude that the intensity at location P, the intensity of the earthquake at location P, is 50.1187 times that of the intensity of the earthquake at location Q. So let's just look at the small amount of assistance that a calculator, in this instance TI-nspire, can give. You can, first of all, you should be able to do 5.2 minus 3.5 mentally, but I've calculated it there to be 1.7. And then it's just a matter of calculating 10 to the power of 1.7. You have a 10 to the power of X button, so it's just a matter of pressing it and then typing or entering 1.7 and pressing enter. And we can therefore conclude, as it says there, that the intensity of the earthquake at P is 50.1187 times that of the intensity of the earthquake at location Q. And so we've answered that question correctly. Question 13 is a functions or applications of functions question. We're told that the number of termites in a particular nest can be modelled by that function there, n of t equals a on 2 plus e to the negative t, where a is a constant that we need to determine, and t represents the time in months since the nest first became a visible mound above ground level. In this model, it's estimated that when the mound first becomes visible, the population or the number of termites was 3 times 10 to the power of 5, which is the same as 300,000. Now, this is a 5-part question. The first 3 parts you can see on the screen there. Part A is a 1-mark question that asks us to determine the value of A. Part B asks us to determine the number of termites in the nest half a year after the mound becomes visible. So in other words, we need to find n of 6. Part C asks us to determine the time in months after the mound becomes visible for the initial population to increase by 130,000 termites and express that time as a decimal. So we're told in the stem of the question that when the mound first becomes visible, the population is 300,000. So if it increases by 130,000, part C is going to ask us to find T such that N is equal to 430,000. Moving on, part D asks us to develop a formula for the rate of change in the number of termites at any time after the mound becomes visible. And an important instruction in the question there is it asks us to express our derivative as a fraction. So as I've noted here, in part D, we need to find an expression for n dashed of t as a fraction. And part E is going to ask us to use the derivative. We're going to be asked to determine the rate of change in the number of termites 5 months after the mound becomes visible, which means we've got to find n dashed of 5. Okay, so it's a 5-parter. Let's go back to the question. In a lot of these parts, in fact, in all of these parts, we are going to be using either n of t or the derivative n dashed of t. So in a question such as this, it's a really good idea to start by assigning n of t to be whatever it is. So if we go to page 1.3 in my document here, before we consider finding the value of A and then subsequently moving through all the parts, the most important way to start this question is to assign n of t to be A on 2 plus e to the negative t. So let's show you how to do that. So first of all, we type in n open bracket t and come outside that closing bracket. The assign command is the symbol colon equals, and it's accessed by pressing Control and then the symbols template. Now notice that our function is in fractional form. So press Control divided by for the fraction template. Then we're going to type in A for the numerator. Notice that in the question, it's uppercase or capital A. You could enter it in, but when you press enter, Nspire automatically changes that to a lowercase a. So don't worry about if there's a mismatch that you see here between lowercase a and capital A, both in the comments that I'm making on the calculator page and also back in the question. And in the denominator, what you would do is you would press or enter 2 plus. Now, a mistake that is sometimes made with the exponential function is don't press letter E. That is going to cause you some grief. Press the backspace or delete button here. You want to add or look at this e to the x key, not letter E. So if you press e to the x, notice that the E is bold and italicized, and it gives you an opportunity to add the superscript or the power. And in that instance, or in this instance, you would type in negative t. So that's how you, and then you would press enter. So that's how you assign n of t. Now, let's first of all look at finding the value of A. So we're told in the question that the initial number of termites in the mound when the mound becomes visible is 300,000 or 3 times 10 to the power of 5. So n naught, the initial number is 3 by 10 to the 5 equals A on 2 plus e to the power of negative 0. In other words, we've substituted t equals 0 into this function and solved. And it's quite straightforward to solve without the TI-nspire. In fact, I would encourage you to be able to do this without the nspire. So basically what you're doing is you're solving 300,000 equals a on 2 plus 1. E to the negative 0 is 1. So that becomes a on 3. So you multiply both sides by 3. And so your value of a, the constant for this model, is going to be 9 times 10 to the power of 5, or in other words, 900,000. Now, if you needed to, you can also solve this equation using the numerical solve command. And the numerical solve command, the syntax is the equation, comma, and you obtain the comma from the comma button down the bottom left of the keypad, comma, what you want to solve for. And to find nsolve or numerical solve, what you would do is you would press menu, then 3 for algebra, and then 1 or enter for numerical solve. And then all you need to do is just enter the equation as I've shown here and complete the syntax by adding comma A. Because there's only one solution to this equation, it's quite safe to use the numerical solve command. And when you solve for A, you obtain A equals 900,000. In part B, what we're required to find is the number of termites in the nest 6 months after the mound has become visible. Mathematically, what we need to do is we need to find n of 6. So we have a look at the top of the page here, my working. I've substituted for A into the numerator of n of t, and I've also substituted t equals 6 into the function. So in other words, n of 6 is equal to 9 times 10 to the power of 5 divided by 2 plus e to the power of negative 6. And when you evaluate that, and I'll show you how you should evaluate that with nspire in a moment, you get 449,442.97 ... termites. You can round that up to the nearest termite, and so we get 449,443 termites according to this model. Okay, so let's show you now how to evaluate this. So on a calculator page or calculator application, it's a matter of just keying in n, and then open bracket, and then 6, and come outside that closing bracket there. Now, I want to evaluate that with or given a is 9 times 10 to the power of 5. To find this with or given symbol, it's the given symbol that's in conditional probability. What we do is we press Control equals, and then navigation pad to the left to highlight the with or given symbol. Then press Enter, and then we say we want to evaluate that with A equals 9 times 10 to the power of 5. You can also type in 900,000, no problems at all, and press Enter. And notice that you get an exact answer. Now, that's not what we want. So in this instance, when we want a decimal answer, instead of getting the exact answer, what you can do is you can press Control Enter, because above the Enter button, there's that sign there, and that's the approximately equal sign. So Control Enter in this instance will give you the required decimal answer, which we can round up to the nearest integer or the nearest number of termites. So the model suggests that there are 449,443 termites in the nest 6 months after the mound becomes visible. In part C, we're asked to find T, the time in months after the mound becomes visible for the population to increase by 130,000. So when the mound first becomes visible, it's estimated that there are 300,000 termites. So if we add 300,000 to 130,000, which is the increase, we want to find T, we want to find the value of T such that N of T is equal to 430,000. So on the top of my Inspire page there, showing you the working that is sufficient to obtain the full marks here. Be good to note down that you're solving 430,000 equals N of T, so A is 9 times 10 to the power of 5, and the denominator is 2 plus E to the power of negative T. We want to solve that equation for T, and when we do so, which I'll show you how to do in a moment, you get a T value in months of T equals 2.3749. Now, this is an equation that just has one solution, so we are safe in the knowledge that we can use the numerical solve command. Now, the way to access the numerical solve command is to press menu, then 3 for algebra, and then 1 or enter for numerical solve. So we can enter in the equation here, which is 430,000 equals. Now we don't need to type in the N of T as is expressed there. Because N of T has been assigned, all we need to do is we just need to type in N of T, and notice that the N is bold and non-italicized, which is good. That is signifying that N is and N of T by extension is representing something, which is good. Then comma T, and then come outside that closing bracket. And then we want to add, because remember when I assigned N of T, I assigned N of T with A. You can go back and reassign it with the value of A, and you don't need to enter this. That's quite a reasonable exam tactic. So here now what we want to do is we've got the with or the given key, and then we want A. We're going to here control equals, and then navigation pad to the left to highlight the with or the given symbol, and then we'll type in A equals, you can either do 900,000 or 9 times 10 to the power of 5, and press enter, and that gives you the time that it takes for the number of termites that become visible to increase by 130,000 from that initial amount of 300,000 to become 430,000. So we suggest that the model is telling us that it takes 2.3749 months for that to occur. In part D, we're asked to find the rate of change in the number of termites at time t after the mound becomes visible. And more importantly, in this wording of the question, it asks us to give our answer as a fraction, so we need to follow the instructions carefully. So TI-nspire can't help here. This is a chain rule differentiation. So we start off with re-expressing N of T as 9 times 10 to the power of 5, which is the constant A, multiplied by, now the way the function was expressed at the start of the question, it was A divided by 2 plus E to the power of negative T, but I've written it as a product with a negative power. it helps to see the chain rule differentiation when we do that. So it's 9 times 10 to the power of 5 times 2 plus e to the power of negative t, all to the power of negative 1. And so our focus is going to be on obtaining a correct derivative of this part. So first of all, using the chain rule, that negative 1 becomes the negative that comes down the front. Our 9 times 10 to the power of 5, that stays out the front. Then what we do is we subtract 1 from the power of 2 plus e to the minus t. We subtract 1 from that power, so that becomes 2 plus e to the power of negative t to the power of negative 2. And what we do is we take the derivative of what's inside here. And the derivative of what's inside here, the derivative of 2 with respect to t is just 0. But the derivative of e to the negative t with respect to t, the negative comes down the front. So the derivative of e to the negative t is negative e to the negative t. Now, what we do is we have a close look at line 2 and we say, we have a product of two negatives. So a negative times a negative is a positive. And we've also got a negative power here and also a negative power here. So we can write our derivative as a fraction with the numerator of a, which is 9 times 10 to the power of 5. And this product is going to form the denominator of n dashed of t. Just making sure that we've already taken into account the negative sign. So the denominator is going to be e to the power of t, because when we bring this down into the denominator, this power becomes positive. And we're going to bring this one down. This is essentially 1 on 2 plus e to the negative t all squared. And so this becomes 2 plus e to the negative t all squared. And that is the form that the question writers require you to express the derivative in. So n dashed of t is equal to 9 times 10 to the power of 5 divided by e to the power of t times 2 plus e to the power of negative t all squared. In part E, we're required to find the rate of change in the number of termites 5 months after the mound becomes visible. So in other words, we've found n dashed of t, and so now we need to find n dashed of 5. Now we can use the derivative in part D, or in this instance, you can use TI-nspire directly. And I'll show you how to calculate n dashed of 5. We have a look at our working up the top part of the page there, that when we evaluate n dashed of 5, we get 1505.87 ... And to the nearest number of termites, and remembering that this is a rate of change per month, so the units are going to be termites per month, that the instantaneous rate of change in the number of termites 5 months after the mound becomes visible is 1,506 termites per month. So let's now show you how to calculate that with TI-nspire. So this is the entry line that we're going to construct, and it looks quite complicated. What we need to do is we need to substitute t equals 5 into the derivative, and also I need to substitute again for a. And if you've already reassigned n of t with a, then you don't need to add this extra substitution. So on a new entry line on a calculator page, what we're going to do is we're going to press menu. Then we're going to press 4 for calculus, and then 1 or enter for numerical derivative at a point. And what comes up is a numerical derivative at a point dialog box. And it's inviting us to, first of all, enter the variable. And the independent variable in this case is t for time. Now press tab. The value that we require here, we're after the calculation of n dashed of 5. So our value is 5. And we're after a first derivative. So we press tab to highlight OK, and then press enter. And what comes up is a template. And what we need to do is we need to add inside here n of t, and then I need to add and a equals 9 times 10 to the power of 5. So inside here, I'm going to type in n, open bracket, t, then come outside just to the right of t equals 5 using the navigation pad. Then I'm going to press the space key, then quickly just type in the word and using the keypad there, AND, then another space, and then type in A equals 9 times 10 to the power of 5, and press enter. So that's how you enter that into TI-nspire. And just, you should be able to see that to the nearest number of termites, it's 1506. But just in case, what you can do, and this is a good illustration for other questions where you've got to round or give answers to a particular number of decimal places. What you can do is TI-nspire has a round command. So I'll show you how to find the round command and how to enter this entry line here. To find the round command, you press menu and then 2 for number 8 for number tools, and then 1 or enter for round. Then what you can do is use your navigation pad and go up to highlight that answer. Press enter to bring it down to the current entry line. Now, the syntax for the round command is the answer that you want to round, comma, to the number of digits you want to round to. Now, if we want to the nearest whole number of termites, in this instance, we would type in 0. So it's comma 0. Press enter, and that gives us the 1506. So it's 1506 termites per month to the nearest termite. And that completes question 13. Question 14, worth 6 marks and is a 5-part question. It's also a applications of functions question where we have a situation that's modeled by a function. A football coach has offered a 12-day intensive training clinic, and during the clinic, the height that each player could kick a football was monitored. One player's kick heights was found to be able to be modeled by the function h of t is log to the base 10 of 10t plus 10 plus 5 for t values between 0 and 12, where h of t gives the vertical height in meters and t is the time in days spent in training. So t is between 0 and 12. There are 5 parts, so let's have a look at the question as an overview. Part A asks us to determine the initial height that the player could kick the ball. So in other words, we need to find h of 0. Part B asks us to determine the training time needed for the player to be able to kick the ball to a height of 7 metres. That means in part B, we need to find t such that h of t is equal to 7. Part C asks us to determine the overall improvement in kick height for this player achieved by that player completing the clinic. So in other words, we need to find h of 12 minus h of 0, and we would expect a positive quantity to the answer to part C. Part D asks us to determine the rate of change in this player's kick height when t is equal to 1.5 days. So in other words, we need to find h dashed of 1.5. And part E asks us to find the training time as a decimal when the rate of change in the vertical kick height is 0.09 metres per day. In other words, we need to find t such that h dashed of t is equal to 0.09. So there are 5 parts, and notice that part C is worth 2 marks and all the other parts are worth 1 mark. So let's have a look first of all at part A. And part A, what we need to do is we need to calculate h of 0. So if we substitute t equals 0 into h, what we get is 10t becomes 0. Log to the base 10 of 10 is 1, and 1 plus 5 is equal to 6. So the initial vertical height is 6 metres. Now, in this question, we have to deal with h of t or the derivative h dashed of t in the 5 parts. So it's a really good idea at the start of this question to assign h of t to be log to the base 10 of 10t plus 10 plus 5. And this time I've added the condition where t is from 0 to 12. So let's show you how to input that. So we come down to a new entry line and we begin by saying, okay, let's enter h of t. Now go to the right with the navigation pad. The assign command is accessed by pressing, you can see it's the symbol for it is colon equals in red there. It's accessed by pressing Control and then the symbols template. Then what we need to do is we need to add in log to the base 10. So if you press Control 10 to the power of x, you can see above the 10 to the power of x button, there's a red log. We have a template. So here, the base is 10, then navigation pad to the right, and we'll add in the argument if you like. So that's 10 times t plus 10. Then navigation pad to the right to move outside that bracket and key in plus 5. And notice that I've also added the condition. So here, the condition, this is the with or the given symbol. It's the same symbol that's used in conditional probability. It's found by pressing Control equals. navigation pad to the left highlights this symbol, the with or given symbol. Press enter, and then we can add in, if you like, the domain. So we'll type in 0. Now to find less than or equal to, press Control equals, and then use the navigation pad to highlight the less than or equals to symbol. Press enter, then T, and Control equals less than or equal to 12, and press enter. So that's how you assign the function, and that's going to end up being a time saver for you in doing a 5-part question that involves this function, because we'll come back and use it time and time again. And to find the initial height, the initial vertical height that the player could kick the ball with Inspire, it's just a matter of keying in h of 0 and then pressing enter, and you get 6. And so h of 0 is equal to 6. In part B, we're required to find the time needed for the player to kick the ball to a height of 7 meters while this player is in this clinic. So what we need to do is we need to solve h of t is equal to 7. In other words, we need to solve 7 equals log to the base 10 of 10t plus 10 plus 5 for t. And I can show you mentally how to get t equals 9, and then I'll show you how to use Inspire to get the answer t equals 9. What you can do here is you can subtract 5 from both sides. So log to the base 10 of 10t plus 10 is equal to 2. Then what you can do is you can say that the left-hand side, rather than 2, is express it as 10 to the power of 2 equals 10 to the power of log to the base 10 of 10t plus 10, which means you get 100 equals 10t plus 10. 10t is therefore equal to 100 minus 10, which is 90. 10t equals 90, and therefore t equals 9. And in fact, you can also see that by substituting t equals 9 in here, 10 times 9 is 90, 90 plus 10 is 100, log to the base 10 of 100 is 2, and 2 plus 5 is equal to 7. So it's quite a straightforward equation to solve. Using Inspire, knowing the behavior of the log function, there is only going to be a one solution. So you can take comfort in being confident in using the numerical solve command. So what we do is we press menu, 3 for algebra, 1 or enter for numerical solve. And then it's just a matter of entering h of t equals 7, and solve that for t, comma t, and press enter, and that confirms that t is equal to 9. So it takes 9 days for this player's kick to reach a vertical height of 7 meters according to this model. Stop. In part C, we're asked to determine the improvement in this player's kicking height over the 12 days of the clinic. In other words, what we need to do is we need to make sure that we've calculated h of 0, which is 6, which is the initial kick height. Then calculate h of 12, which according to the model is the final kick height at the end of the clinic. And I will show you how to evaluate that in a moment. We get 7.11394 meters. And the increase in kick height, or the improvement in the kick height or the kicking height over those 12 days, is calculated by determining the difference between h of 12 and h of 0. In other words, h12 minus h0. And when you do that, the kick height increased by 1.1139 meters during the clinic. So this is quite a straightforward calculation with h of t already assigned. So this question's worth 2 marks. So I think I'd be careful, and I would write down what the value of h of 12, and I would also write down the value of h of 0, and then I would write h of 12 minus h of 0, and then give the answer. So just enter those with TI-nspire, and then note your solution down like I've done here to part C, and that should be able to give you the opportunity to obtain the 2 marks that are on offer. So the kick height increased by 1.1139 meters during the clinic. In part D, we're asked to find the rate of change in kick height when t equals 1.5 days. In other words, we need to substitute t equals 1.5 into h dashed of t. Now, in this question, h of t is a log function, log to the base 10. I wouldn't advise you trying to differentiate. It's a very difficult derivative to obtain. And this question is only worth 1 mark. So we can do it directly on TI-nspire. And so when you calculate h dashed of 1.5, you get an answer of 0.17372, and the units are meters per day. So that is the rate of change when t equals 1.5. H dashed of 1.5, which is 0.17372 meters per day. So let's show you now how to obtain this, or construct this entry line here. So we're going to press menu, then 4 for calculus, 1 or enter, or numerical derivative at a point. And up comes the numerical derivative at a point dialog box. The variable in this instance is t. Press tab. The value is 1.5. Press tab. We do want the first derivative, so we press tab again to highlight OK, and then press enter. And so all we need to do now is to complete the template, and we achieve that just by typing in h of t, press enter, and we get our rate of change at t equals 1.5, 0.17372 meters per day. Alternatively, if you go to the catalogue, press the catalogue button, press number 5 to go to the symbols template. You can also use the derivative template, which is highlighted there. Press enter. It's slightly longer because what you have to do now is you have to type in the t for the independent variable, and then navigation pad to the right to type in h of t, and then navigation pad to the right outside there. Then you've got to press Control equals, navigation pad to the left to highlight the with or given symbol, and then type in t equals 1.5. Press enter. Okay, so there's the 2 ways of performing that. And also, if you press Shift minus, that also gives you the template for the derivative, and you can fill it in as I've done for those two previous entry lines. So we've completed part D. H dash of 1.5 is 0.17372 metres per day. In part E, we're asked to determine the training time when the rate of change in kick height is 0.09. Now, as you can see by my working, and it's only worth 1 mark, all we are required to do is to solve h dashed of t equals 0.09 for t, and we get 3.82549 days. Now, let's see how we enter in this rather complicated looking entry. It's not as complicated as what you might first think. So on a new entry line, what we're going to do is we're going to press menu, 3 for algebra, 1 or enter for numerical solve. Now, we can be quite confident that we can use the numerical solve because there's only one solution. We can tell there's only one solution to this equation. Now, we need to key in d dt of h of t. And the best way to do that, I think, is if we press shift minus, which is the shortcut. You could also go to the catalog, press 5 for symbols template, and there's the derivative template there. So I'm going to press escape. Type in t here, which for the independent variable, navigation pad to the right, and then key in h of t. So in TI-nspire language, if we compare d dt of h of t, that's h dashed of t, then press equals, and we set that to be 0.09. We want to solve for t, so press comma, then t, and press enter, and we obtain the required answer. We could also solve this graphically. So on a graphs page, this illustrates the finished product. In f1 of x, what you can do is, because we've got h of t already defined, h dashed of t in terms of this graph page is represented by d by dx of h of x, and f of x is that horizontal, or f2 of x is that horizontal line 0, y equals, if you like, y equals 0.09. And just for completeness, I've just added the domain constraint there, that t, and on the graphs page, it's represented by x, lies between 0 and 12. Now, to enter that in, if I press backspace there, and I can type in 0.09, and then it's control equals, navigation pad to the left, press enter, and then we want to say, all right, we want to graph that between 0 and 12. You can see there you've got endpoints. The derivative is not defined, you can't tell, but the derivative is not defined there at 12. So now we type in 0, control equals less than x, control equals less than 12. That's how you key that in and press enter. Now nothing changed because I keyed it in correctly. And what you need to do then is to find the intersection point of those two graphs, the derivative function and also the horizontal line. So on a fresh page, I've managed to set the viewing window as such. If we press tab, what I can do is assume that they've been entered. So the best way to enter that for f1 of x is to use either the shift minus shortcut or to use the catalog. All I need to do is just click inside there and the graph appears. Then press enter. Then just to make sure, repeat, click in there. Then go down to f2 of x, click in there. And now to find the point of intersection, if we press menu and then 8 for geometry, 1 or enter for points and lines, 4 for intersection points, click on the first graph, click on the second graph, and that gives us our intersection point. Press escape, move that, and if you notice, compared to page 1.8, there's a few more decimal places that we have available to us. That's because on page 1.8, if we go to menu and then the settings, we can change that to float 6. Press OK. And then go to page 1.9. And we're also in float 6.